Hi there, it's Clint Mason with Guys and Well Solutions. Just got a short presentation on some rules of thumb and picking the right plunger, or some ideas on how to help you pick the right plunger type for each well. So let's go through this, see if we can get this done in under 15 minutes. So when we talk about plungers rule of thumb, the rules of thumb is, as I like to call them, are really just a starting point. And what that means is they're very safe numbers. You typically can just plunk them in on any well or most any well, and you can start to cycle a plunger. It's definitely not optimized. It's not the optimized point. It's a place where you can start. So once you get it started, you can look at how the well's reacting and casing and tubing pressures, and from there you'll start to fine tune your settings. Your fall time, we'll talk more about that. You have to be careful. If you set that too short, you're not going to let the plunger get to bottom. There's a lot of ways to find out how that plunger is falling. One is using an echometer and chase the plunger down. The other is kind of a little trial and error where you continuously shorten up just a little bit, a few minutes every day, until you start seeing a significant change in the way the plunger runs. Either it comes up a little faster, or the well pressure starts to build up on the casing because you're not lifting the fluid out of the well as good, but you can kind of fine tune it that way. It just takes a little longer to do it. There is many factors that impact the rise time and the fall time and overall plunger performance, of course. And every well really needs to be evaluated on a per well basis. Pressures can impact it, fluid volumes can impact it, variations in the line pressure can impact your final settings. So all of these need to be reviewed. Now, shut-in time and optimizing the plunger cycle. Probably one of the key things, especially when it comes to vertical wells, is your off time can really impact your total production time per day, and can really impact overall performance. Horizontal wells, it's a little different story, but we're just going to stick with some fairly basic rules of thumb on uh, to start with, without getting into the differences between horizontal and vertical, and the reasons why we may want to have more shut-in time than you would, think is required. But anyway, some rules of thumb, conventional. Uh, Most plungers, conventional, no, so to reiterate, a conventional plunger is a plunger that doesn't have a bypass valve in it, or a hole in it, or a extra port that can increase, so like a two-piece plunger where you have two pieces that come apart and it can fall very fast. So it's a solid plunger, or without any extra bypass. I typically use about 50 meters per minute fall speed, or 100. It's about 150 feet per minute. And you just take your well depth from surface to spring, and you divide it by 150 feet per minute if it's in feet, or you divide it by 50 meters per minute if it's in meters. And that'll give you approximately the number of minutes you need to get that plunger to bottom. And again, this is a safe number, not an optimized number. Now, I also use for most conventional plungers, a range of 215 to 350 meters per minute rise speed. And that's what I consider kind of a safe range to run the plunger in. It can definitely come up slower and still be very efficient. And it also can sometimes come up a little faster. But what's happening is, when you start going a little faster, you're starting to put a lot of kinetic energy into the wellhead, and you're going to start damaging springs and different things like that. Now, the other thing is, do the different plunger types really impact how fast it should come up? And in my opinion, it does. A conventional, we'll call it a ring type, solid type plunger, you typically want it to run a little faster than say a pad plunger, because of the different seal efficiencies. And the reason a plunger, basically the faster the plunger is running, it really indicates how much gas is flowing past the outer edge of the plunger, and really how efficient the seal or the interference is that you're creating. So a more efficient plunger can typically run a little slower and still be very efficient in its lifting abilities. So anyways, so somewhere between 750 feet per minute, 850 feet per minute, somewhere in there is a good target for your plunger coming up. Rules of thumb. Now I'm going to call it ventral max, but you venturi. There's several different things. I think rattler, different things where they have basically a small hole in them that allows extra bypass area or flow through the plunger. My experience is, and of course, there's different. You could have a very large hole and it would fall faster, but base this on basically a quarter-inch hole or bypass port through a plunger. And I use about 70 meters per minute fall speed, and it's somewhere, 80, 70 meters per minute is probably a pretty safe number to use. So that's about 225 feet per minute fall speed. And rise speed, I've actually got it a little faster than a conventional plunger, mostly again because that extra port area, you want it to be travel a little quicker, which would indicate that it's supporting the fluid above it as well a little better. It doesn't necessarily mean that's the ultimate optimized speed, but I typically try to start out that way and making these types of plungers travel the surface a little faster and then optimize from there. Rules of thumb for a free cycle. Now, a free cycle plunger is a plunger that has a valve inside of it. So, it might be a rapid flow, and there are 3 slot and 4 slot. There's people have a lot of different names. But basically, you've got a valve, and through that center, you activate that valve, whether it's a rod hanging in the lubricator or there's a rod built into the plunger that pops open that valve, gives it a large bypass area, and allows that plunger to fall. Now, I typically use about 375 meters per minute, and all of these speeds are based on the well being shut in, not the well flowing. So this is a shut-in fall rate. Now, some free cycle plungers will fall faster than that. Some fall a little slower, but the plungers that I use, that's kind of the safe number that I typically use. Now, so that's about 1,250 feet per minute, and your rise speed is somewhere around at 800 feet per minute as well. It's a kind of a target that I use. So it's anywhere from 190 to 250 meters per minute, or around 800 feet per minute, somewhere in there. Now, again, the note is free cycles have a really wide range of speeds. You probably need to, if you're trying different styles of plungers, different manufacturers, you'll probably need to chase them with an echometer or something to get a really good understanding of how fast they fall. But some can fall extremely fast and some don't. We've seal types, salt, there's pad, there's brush. I talk about seal types in another video, so we're not going to go through that too much, but let's go through there. Now, two-piece ball and sleeve or pacemaker type plungers. One of the critical things you need to understand is that the velocities in these plungers can become extremely high. And I've tracked these plungers falling in excess of 5,000 feet per minute in a well. Had a well that was about 5,200 feet deep, just a shallow gas type well, and the plunger was hitting the bottom hole spring in about 48 seconds, and it was hitting it so hard. This is again with the well closed, that you could feel it shake at surface. Tremendous amount of kinetic energy can be put in, can be generated with these plungers with those kind of velocities. Even though they're lighter than a standard plunger, it's the velocity that really creates that kinetic energy. So a couple of things. First of all, proper sleeve and ball weight should be used. Now, there's titanium, there's stainless, there's some steel, and the ball can be made from several different materials, right from ceramic to tungsten carbide. There's even a one time I've seen some balls made from basically spent uranium, which was extremely heavy. And the idea is that that weight is going to let that ball fall against flow, because the very next thing we talk about is you should never drop these balls with the well shut in. So typically you would shut the well in just long enough to allow that sleeve to come off the trip rod that's hanging in the wellhead. Once it's into the tubing again, you want to open it up again, because to reiterate that, these plungers can reach huge velocities. And, you can say, oh, I'm just going to leave it shut in for a minute, but in a 5,000 or maybe even, 5,500 foot deep well, it's going to hit bottom, or could hit bottom, before you turn that well on. And, you could do some kinetic energy calculations, but it can be in the tens of thousands of pounds of force on those little springs. Obviously, there's a bunch of fluid that helps slow it down and things like that, but I've seen so many bottom hole springs and plungers destroyed by people leaving a minute or 2 minutes of close time because the ball and plunger weren't making it to bottom, or the ball was floating and stuff like that. So, you know, in all of your optimization with a two-piece plunger, you really need to make sure you have the proper ball and sleeve weight for the flowing conditions. Heavier if it's stronger, higher fluid; lighter if it's less fluid and probably lower flow rates. A rather really interesting thing when you're looking at your wells, and we've really, really noticed this as we've been working a lot with horizontal wells, where we're getting a really wide range of pipeline pressures. And we're working in fields where one end of the field might be 700 kPa or 100 psi or 150 psi, and on the other end where they're still doing a lot of drilling and infrastructure, it could be over 1,000 or 7,000 kPa, over 1,000 psi or over 7,000 kPa. And it came up because guys were using these rules of thumb that I was throwing out at them, which are based, around 250, 300 psi or less kind of idea. And they couldn't get the plungers to operate properly when they were in the higher pressure areas. And it really is because of this. So you can see here, we did some tracking. Here's your, pressure at close, pressure at plunger to bottom, the depth. These are meters, bottom hole spring, I mean. And these are kind of the pressures that we were looking at as it was falling. And here's our average fall velocity is in meters. Now, here's our free flow ring plunger dual service, and it's falling around 304 meters per minute in gas. Here's some gas densities. And then if we look at the pressures as they increase, like here's an example, 5,400, we're only falling at an average of about 60 meters per minute. Well, up here in this 3,165, we're falling at, 84, 85 meters per minute. And here we've got 3,100 kPa, and we're, 77 meters and 79. So you get this up to 7,000 kPa, and you'll see that this fall rate drops below that 50 meters per minute. But it gives you an idea how, um, that 50 meters per minute rule of thumb for these type of plungers is a very safe number. I mean, the plunger should be at bottom long before that, unless you're got a very high fluid column, or you've got a very high bottom hole pressure or a tubing pressure, which is going to slow it down. But you can see these are just examples of how the plunger is falling. So. So some basic rules of thumb, conventional plunger. Again, fall speed is 50 meters per minute or 150. Rise speed is, good target is 250 meters per minute or around 800 feet per minute, 850. And to do that, it's just well depth divided by 50 equals minimum close time. Plunger target or rise time, well depth divided by 250. That's how fast you want it, the target you wanted to come up, should give you an estimate on how long it should take for that plunger to come up. Then when is a plunger traveling too fast? When is a plunger traveling at a danger speed? These are fairly arbitrary and kind of based on an average, but you need to speak to your plunger lubricator manufacturer to understand what the lubricators are designed for, the kinetic energy absorption. But I typically use a fast plunger arrival as 350. And what that means is if I'm getting repeated continuous fast plunger arrivals, maybe I get 4 or 5 or 6 or 7 of them, and we're recording that, that would start something to happen, a maintenance cycle. We want to go out there. Why is this plunger coming up this fast? Inspect the top spring and things like that. So it's a trigger, and it might be a multiple impact trigger. Danger plunger speeds to me are if we're running that plunger over 450 meters per minute on average, or it comes up once that speed, it should probably trigger a reaction, which is we should go out and first of all understand why it's coming up so fast. Chances are the plunger's hanging up on something like paraffin or asphaltene or hydrate or something. But one time, above this speed, and really that lubricator should be opened up. Top spring should be inspected and make sure there's no damage. And it doesn't hurt to look at the plunger and make sure that you're not squashing or crushing the fish neck or other things like that as well. So these are kind of trigger points, but these trigger points are going to change a little bit depending on lubricators because all lubricators are not the same. And some lubricators, this could be exceeding the, and depending on the weight of the plunger and things like that, it could be pushing that lubricator's design, and you could be stretching threads and damaging it. Other lubricators just could be nothing, and not as they're just built in a way, heavy material and flange and things like that, where it's not really a concern, but it probably is going to start damaging your top spring if that's the velocities you're seeing. So this is always kind of a difficult conversation to help for people to try and get their mind around what's happening. So I've got a conventional plunger cycle. So basically, during the rise or open cycle, that's the time you're waiting for the plunger to come up. The plunger is traveling up in a conventional plunger, easy to understand. During the delay, plunger's at the lubricator, it's sitting at surface, and then when you close in the well, the plunger falls. And you need to be closed in long enough for that plunger to reach the bottom hole spring. Now your closed might also be impacted by how long it takes for that well to build up enough energy, pressure, to kick that plunger back out again. So the plunger could sit at the bottom on top of that bottom hole spring for a period of time. Then we have a free cycle plunger. Now we have a close time, and a free cycle may have part of its close time where the plunger is falling, and then part of its rise time, or it clicks back to open. So maybe you're only having to shut that well in for 2 or 3 minutes, but it's taken the plunger 5 or 6 minutes to actually get to bottom. And you might be able to open it up before the plunger gets to bottom, and it'll continue slowly going down, reach the top of the spring, close the valve, and come back up. So you can have a cross of where that plunger is falling. It can be in closed and in rise. And this is an example here. So it's falling, it's closed, it's partially in the closed cycle, and it's finishing the fall. It's fall in the rise cycle, hits the bottom hole spring, turns right around, comes back up, and then it goes into delay and then back into closed and kind of repeats these cycles. Now, the reason that's important is that back up to this conventional, your rise time is pretty easy to understand. If the well is so deep and we want, say, 250 meters per minute, let's say it's 5,000 meters deep, we're basically looking at about, what would that be? It's not 5,000 meters deep, sorry, 1,500 meters deep. We'd be looking at 4, 5, 6 minutes for that plunger to come from the spring to surface. So it's easy to understand that. But if part of your rise time is the plunger is still falling, maybe it takes 4 or 5 minutes for that plunger during this rise time before it gets to bottom, which then adds to the rise time. So instead of coming up in 6 minutes, it might actually come back in 10 minutes, which is still good. It's working exactly the way you want it. Its travel time is good. And then it goes into delay. But here you might have an hour delay. Here you might only have a half an hour delay. But when you look at your total production time per day, it's quite different. So one cycle per hour, 12 hours of production per 24-hour period, and that's a rise time of 8 minutes in this well example, delay time of 22 minutes, close time of 30 minutes. If we do 2 cycles per hour with a free cycle, we might be able to get a rise time of 15 minutes. See, it's a little longer because part of our fall time is pushed into the rise. A delay time of 10 minutes, and a close time of 5. And that ends up giving us 20 hours production per 24-hour period. And then we get into the two-piece plunger, which really should almost have zero close time in it. And the close time, this little tiny sliver you see here, is going to be just long enough to get that plunger out of the lubricator. So it could be 10 seconds or 30 seconds or whatever. Really depends on how fast your valve closes and opens again. So it takes 30 seconds for that valve from its signal to slowly close, stop flow long enough for that plunger to slip out of the lubricator and open up. That's your close time, 30, 35 seconds. If it happens very quickly, you've got a little Kimray valve right on your wellhead, very close, and it reacts, shuts in a few seconds, then you only need 5 or 10 seconds of close time. But during the entire fall time, okay, the plunger is falling actually when the control system is in rise because it's gone back into open and it's waiting for that plunger to show up. So it's the rise or the plunge. So plunger's falling, it's falling while it's flowing. It gets to bottom, hits the bottom hole spring, and then it turns around and comes back up. And then it shows up and then you get into delay. Now what's interesting with a two-piece plunger, you can have a rise time that might be 20 or 25 minutes, which is including a lot of the fall time and kind of coming back up. And you might end up having only a very short delay time, 2-3 minutes. So your total production time is kind of still happening, but it's a lot of it is captured in the rise time or the plunger open time, and a very small part of it is in the delay time. And one of the big things with a two-piece plunger is that your delay time has to be long enough. So the delay plunger comes up, it knocks that little ball off the bottom of the plunger, and that ball starts falling down. In Depending on the type of plunger two-piece you're using, you need a certain period of time of separation. I use a rule of thumb of about 1 minute per 1,000 feet of depth. So if the well is 10,000 feet deep, you need to have a minimum delay of 10 minutes. And that's to ensure that that ball will slowly, as it's falling against the flow, it's going to get down far enough that the plunger won't catch it. Because a plunger should fall faster than the ball in most two-piece plunger applications. So if I came up, knocked the ball off, only flowed for a minute, shut it in again, that ball, to let the plunger take off, that ball is falling at 400 or 500, whatever, 1,000 feet a minute, and the plunger is falling at 1,500 feet a minute. Well, within 2 or 3 minutes, or with the well flowing, it catches up to each other, and then the plunger comes back before it actually reached the bottom, missed the fluid, or whatever. So you get these very erratic run times. You'll get a fast run, slow run, fast run, starts jumping around because the flow rate will be higher one time after it's cleaned the tubing out, will be higher the next cycle. So the plunger actually floats and doesn't make it down, or the ball floats and it makes a quick cycle. And then the flow rate, of course, is going to be lower because you've loaded the well up. Then the plunger and ball falls farther and maybe grabs some of the fluid. So you get these really very erratic plunger runs. Typically, you know, you just need to increase your delay time a little bit, or look at the plunger weights. Are you running too heavy a plunger, too heavy a ball, or a combination might be not quite right, or sorry, too light of plunger, too light of ball, so it's actually not it's not letting that ball fall because it's a titanium ball and it's just falling very, very slow because there's too much flow. Well, if I make that a stainless steel ball, it's going to be heavier, and it's going to fall against more flow rate. Or I go to tungsten carbide, it's going to be even heavier and it's going to really fall. But then I've got to match the plunger. The plunger's got to be heavier as well as the ball gets heavier, which is the proper way to cycle two-piece plungers. It can be a little bit confusing, but this is kind of key as you're going through each plunger style. How do you make it run? Where is the plunger? Where are you putting your open time, or production time, which is a combination of delay and open time or rise time? And what does the plunger do during the close time? So you can see it. Every plunger has a slightly different mindset you got to be at. So just to bring this up quick, so understanding energy, pressure, or load work, and when in the control system. When we reduce close time, we decrease lift energy. Casing pressure doesn't build up as much. When we increase afterflow or delay time, we increase the fluid load. So that's how, if we do either one of those things, we're going to actually make that plunger travel slower. And we should increase the daily production time. Okay. When we increase close time or we decrease delay time, so we increase close time, it's increased lift energy, or we decrease delay time, which decreases load fluid, we're uh, we're going to start to decrease daily production time. Plunger is probably going to come up faster. Plunger is going to go slower. So if my plunger is coming up too fast, I want to do one of these things. Typically, I always reduce close time first to its minimum, and then we will start to increase the delay time. If I need the plunger to come up faster because it's loading up or not keeping up, then I would do this. And I would typically decrease my delay time first, then increase my close time. And I always do it in that order. I don't do both at the same time. You always want to do one, then the other, and then either way. How do you decide what plunger is best for you? Well, I get this question a lot. So the quick trip two piece, again, we kind of explained it. It has some, I would call some rules of thumb. It can lift quite a bit of fluid, more than 100 barrels per million. They have a quicker fall time. They may require some tubing head modifications. They're more expensive to operate than obviously a conventional plunger. They should be inspected at minimum every 3 months. I would even say more often if it's a very you're making lots of cycles per day. And these will typically run with packer and slim hole completions because a quick trip plunger is a what I kind of call a velocity plunger. You basically are using, or I use critical rate. So if I can maintain that well's flowing when I get the plunger running at about 60% of wellhead critical rate, it's a good quick trip or a two-piece plunger application. If I'm below that, it's more of a GLR, gas to liquid ratio. We got to build up energy and use that energy to shoot that load out of fluid by using pressure differential, and that's a little different mindset. And we use gas to liquid ratio. The old rule of thumb of whatever 600 standard cubic feet per barrel per 1,000 feet depth, or 400 or 800 or 1,200, depending on who you talk to, is kind of the what we would use. Now, Venturi, they fall somewhere between 20 and 40% faster than conventional. And so in between a quick trip that might be falling quite fast is Venturi, just speeds it up a little bit. Now there's some other um, potential benefits that people have talked about. I don't know, some are there, some are not. But the main thing is they can fall a little faster. They're also going to be less efficient because they do have a ported area through them. And conventional plunger has limited number of cycles per day. It requires fall time of at least 1 minute for every 50 meters of well depth. Again, that's not the optimized number. That's the rule of thumb number. That might be, maybe that plunger's falling at 70 meters a minute, but you have to figure that out with your optimization strategy. They have an overall lower cost of operations typically. You can probably get away with inspecting them every 4 to 6 months, depending on the style. Of pad plunger with multiple parts, you would inspect more often than a solid plunger. Um, they typically result in less production time in a 24-hour period over other options, and they work best with good pressure, and they also work better without a packer in the hole. Typically, this isn't a vertical well, because you're not looking at that good inflow. You're actually trying to store that energy. So you need that annular area to let that well build up and store that energy and that cushion to drive that plunger out when you open it up next time. That's why you don't want a packer in a hole with a conventional well. So now I've got this well, and here's an example that I brought up. And to help me kind of initially determine the type of plunger that I might use. So here's an example. This well has a very aggressive buildup, and then it tapers off and kind of flattens out. So to me, when you see this kind of a pattern, it's probably a pretty good indication that a free cycle or a two-piece might be a good type plunger because you have a really good inflow. Now, lower pressure wells, you'll see this with good deliverability. You'll see this quick buildup. It tapers off and it becomes very, very slow. Will almost flatten out. And if there's a build, like if it comes right up here and it kind of flattens out and slowly builds, it's probably you squeezing fluid out of the tubing more than the well building up anymore at that point. And this is your tubing pressure we're looking at. So when I see a buildup pattern like this, I'm going to go, hey, I think a free cycle might be the right one, because a conventional plunger, it's way back here when it gets in, where it's going to reach bottom hole, and say 30 minutes to get to the bottom. But our majority of our buildup is done in the first 5 to 7 minutes. So all of this other time is really quite likely lost or build lost time that could be the well could be producing. So this is a pattern you would look for. Now in the next example coming up here, um, right here, we have a well, and it doesn't build quite as fast. No, you first shut it in, and with the first minute or so, it snaps up 100 psi or 50 psi. And then it just slowly builds and builds and builds and builds and builds over time here. In this type of example, I would look at this well and say, you know what? This may be a better conventional plunger because we've had to shut the well in for at least 30 minutes to get close to our maximum buildup. Now, so that's probably where I would take and I'd say, oh, this matches the conventional plunger falls time. It's probably a good plunger to start with. Now, this is where you really earn your well optimization merit badge, I guess. We've identified that the conventional plunger is probably a good starting point. One of the things that you have to, when you're looking at optimization is this little buildup here that kind of snaps up. We could definitely, it kind of falls within that free cycle range. Now, if I was looking at this well's total production, I don't have a graph on here, and I was to pull up my critical rate chart that you should have that gives you kind of an idea what your critical rate is in the tubing in a particular tubing size and particular pressure. And if my flow rate, my average flow rate per day was greater than 60 or 65% of the critical rate, daily critical velocity required, production required for that well, that to me might push me back towards a free cycle because I might be able to cycle that plunger many more times and only worry about this little short buildup. And and that's really the optimization opportunity here. But initially, when you're starting the well out, it might look like a conventional plunger. Once you get that fluid moving and cleaning up, your velocities or your production starts coming up. Then you can say, oh, again, hey, I'm within 65% or close to that 60% of my wellhead critical rate on a 24-hour period. Hey, let's look at trying a free cycle or possibly even a two-piece. So that's how you really look at optimizing a well. So some important points: excessive fall speeds, excessive speeds shouldn't be fall speeds, but excessive speeds where the plunger is rising or falling will damage the equipment. Your plunger manufacturer can provide those maximum speed targets for both your bottom hole spring and your lubricator. You should match the plunger to the buildup of the well to ensure to minimize excessive close time. So like we were just talking about, if your well builds up, basically full in 5 minutes, well, don't put a plunger in there that's going to leave the well shut in for an hour. Look for one that you can get that well back open a little faster and try to minimize that lost production. Once your tubing build is stopped or is very slow, you should be looking to open and full the well. So again, match that plunger to fall rate to the well buildup. The rule of thumb is not the same as optimized time, and it's only a safe point to start your optimization journey. So those are a couple of important points. Now, vertical well versus horizontal well, kind of a recap. It's very clear that working with optimizing plunger is much different between vertical and horizontal well bores. Horizontal section is constantly slugging fluid along the casing liner. There's all sorts of things going on downhole. So when you're making a plunger choice, you have to consider several other factors. One of them is that in a horizontal well, many times, even though you have a well that's very strong, it can build up or has the energy to run a two-piece, for example, you may not be getting the best production from the well without a little bit of shut-in time, because that little extra shut-in time or build up of pressure actually helps you move fluid through the horizontal, through the transitional into the tubing. And you can see that your plunger may actually work better with off time in a horizontal well. Typically vertical wells, total hours on per day results in more production. Horizontal wells, that's not necessarily the case. I've actually seen many wells that produce more with a little more off time in a total 24-hour period. All right. A lot of the production is done in the secondary slug in a horizontal well, where on a vertical well, you'd probably pick most of the liquid production up here. Well, and this is basically well shut in, well opens up, plunger's traveling to surface, fluid hits surface, fluid unloads on the top of the plunger, plunger surfaces, then you'll get a gas flow. Well, somewhere in here on a vertical well, we would probably shut that well in and make another cycle. In a horizontal well, many times during that gas flow, you're actually moving that fluid out of the horizontal into the tubing, and you're looking for these big secondary slugs. And that could be 80, 90% of your total production per cycle instead of being over here on the plunger. Now, I bring this up to show you. So here's a two-piece plunger. It was running in the well, had lots of velocity, but the problem, lots of velocity in the well, the flowing well, so it could support it. But the problem we were having, and this is in a vertical well, is fluid slugs were coming in and really changing the way the well was flowing. And those fluid slugs were catching the ball and sometimes hanging it up high, not letting it get to bottom. Then the plunger would run down and catch it part way, and then it would come up and stuff. So it was very hard to get it to run consistently. And we tried heavier equipment or heavier ball and sleeve. We tried lighter, tried all sorts of different things. What we found was that we really needed to have some off time to ensure that the plunger could get to bottom. And in this case, we basically gave it about 10 minutes of off time per cycle. And you can see that it just leveled things out. We went from a two-piece to a free cycle because I don't ever believe in dropping a two-piece to the spring when it's not flowing because of the damage I've seen. But a free cycle falls slower, and they'll typically handle the impacts, especially if there's lots of fluid. But here you can see once we put that free cycle in, it just leveled off the production because it was making it to the top of the spring every time. And this was the impact. Sorry. Here's our leveled everything off. And here's the impact to our actual tubing pressure. So here it's very erratic, and or sorry, casing pressure is very erratic. It's going up and down is depending on where the fluid level was, where the plunger was coming from, and then it just leveled right off and stabilized. That's the difference and in between these two plungers in this example, where a little off time actually increased production significantly. And that's about 5E3, which is about 150 MCF a day, and close to 24 barrels per day of fluid increase between those. That's a two-piece and that's a free cycle. Doesn't always work that way, but in this case, it made a big difference. That little bit of off time really made a huge impact on the well's production. Anyways, that's my review on kind of rules of thumb and plungers, fall times and settings and stuff like that. Some very general numbers. Uh, Thank you. If you'd like more information, reach out to info@kaizenws.com, which is KAIZENWS.com, or check out our website at www.kaizenws.com. Have a great day. Be safe.